In a fit of completeness speaking, the end of class Monday, I said, well, we'll look at more stuff on Wednesday. And then I look at the schedule and it says, oh, today's question and answer day. So that's for 7.4 and 7.5 rather than me starting 7.6. So instead of starting 7.6, I've got what questions do you have for 7.4 and 7.5? Because I realized I'd scheduled those 2 days backwards from what I thought. Oops. So chapter 7, section 4, partial fractions, 7.5, integration strategy. What questions do you have? Yes, sir. $54 from 7.4. So grab that problem. $54 says, use integration by parts together with the techniques from this section. So x times inverse tangent of x dx. So my first question, if I'm going to use integration by parts with, what's u, what's dv? That's the first issue. Because if I go through that anagram, mnemonic, logarithmic is first, inverse trig comes before polynomial. Trig comes after, but that's an inverse trig. So that's a better choice for you. If I do what you suggested, Jacob, if I write u equals x, then du is dx, but then dv is tangent inverse of x dx, and I don't know how to integrate that. So that's not helpful. But if I go the other way, then what's v? And what's du? How come the trig formula sheets? Yes, absolutely. Let's pull that sucker out. It's on canvas. Great. So, formula for integration by parts. The integral of u dv is uv minus the integral v du. Disgusting, right? But, wrong but. That right-hand integral, I take the 1/2 out, I can write that as x squared over 1 plus x squared. And that's a rational function, isn't it? Okay, now I see a game to play with partial fractions. However, bottom doesn't factor, right? 1 plus x squared doesn't factor into anything. It's already, without going to complex numbers, it's as simple as I can make it. So I look at the degrees. The degree at the top is x squared. The degree at the bottom is x squared. The degree at the top has to be smaller to do partial fractions. I got to divide. Let's do the division, but this one has a sneaky trick too. If I was going to divide, I'd have to divide the bottom into the top. I write it in the other order just to make that easier. X squared into x squared goes once. Subtract all of that, I get a -1, that's my remainder. So, instead of x squared over 1 plus x squared, I get 1 plus -1 over x squared plus 1. You ready for the sneaky version that avoids having to do the division? I'm going to add 0. How am I going to add 0? I'm going to add 1 and subtract 1. Then 1 plus x squared over 1 plus x squared is 1. And I have -1 over 1 plus x squared left over. Now I know how to integrate, right? That goes up here instead of doing partial fractions. I already know what the integral of that is. Instead of having to do partial fractions at all, once I do the division, I don't have to do partial fractions. Whew. But this is what I meant by in Monday's section where I can do weird things, but I always go back and do the algorithm version, right? If you see a shortcut, you're welcome to take it, but you don't have to. Better, Jacob? All right, more questions. Ask me more things. Yes, Matt.
Can you do 7.4
20.
It was just the factoring of Austin.
Okay, so can you read me the original problem? It's the integral of
The integral of x times 3 minus 5x over 3x minus 1 times x minus 1 squared from 2 to 3.
So the ugly part of this is the partial fraction setup. So I have a linear thing squared, right? So that means that when I do this as partial fractions, I'm going to get 3 fractions. One with the 3x minus 1, one with x minus 1 to the first, one with x minus 1 squared. How far did you get from here?
There, and then I tried to expand it out and do like the a x minus like find a common denominator.
So that's got 3x minus 1. It doesn't have the x minus 1 squared. This has the x minus 1, but it's only to the first, so I'm going to get another x minus 1, and then I'm going to get the 3x minus 1. This already has x minus 1 squared, so it's just going to get the 3x minus 1. And then over here, I'm going to get x 3 minus 5x.
So you don't have to do like times
If I did, then over here, I would actually have an extra x minus 1, wouldn't I? Yeah. So this is a case where you used a common denominator, but then not the lowest common denominator. And that's not wrong, it just gives you an extra bit with the x minus 1. But what that means is that that coefficient is 0. And that would still work, and it would turn out to give you the correct A, B, and C, but you had an extra number floating around. Yes. I tend to multiply through by whatever denominator is on this side to get rid of it. So if I multiply by all of that, I only need the x minus 1 squared. I only need the 3x minus 1. Yay! The calculus isn't the hard part. The algebra sucks. The older version of the TI calculator had a button that said solver. They got rid of it and built in different programs, but because I can do this as a matrix, once I have the equations, but getting from there to here used to be automated in that solver button, but it isn't anymore. I'm sure somebody out there somewhere wrote a partial fractions program. If you have a USB-C to USB micro cable, you can get the TI software for your computer. TI Connect, that little blue and green arrow box, it's available at the TI website. And then you can download a program that will work on your calculator and send it to your calculator. Hey, people, I'm telling you that you should be using this technology, right? If I'm using this technology, program the hell out of it. I would point out to you that the list of programs I have in this thing includes a lot of crap we don't do very much that we could. The whole idea is that I want you to be able to get to the point where you can solve things. If this helps, use it. If it does it for you, then I'm going to go, how the hell did you do that? Okay. More questions? Yes, ma'am. Yes, over here, I would write this as 3x minus 5x squared. And then once I multiply all of this out, I'll have the x squared term, the x term, and the constant. I'll have the x squared should be, nut coefficient should be minus 5, the x should be 3, and the constant should be 0. You're welcome. Yeah.
75, number 66.
Number 66 and 75. Ln of tangent of x, that one?
Yeah.
Okay. From pi over 4 to pi over 3. Well, that's unpleasant looking, isn't it?
Yes.
But I see ln of tangent, and my brain says, that's a chain, well, I should do a u sub. Talk to me.
I mean, like sine and cosine. The other side, cosine pi, sine x, cosine x.
Okay, so if I write that, what do I do from there? There are several options.
I think if I put it, say u is like cosine x, and du to be minus sine x, and how can you make square for du in both of those? I'm trying to make sure.
That's my problem. I don't know how to deal with a du down here as well as a du up there. So that's not, I'm not sure that that's the right direction to go. But I'm not unhappy with this idea. As a matter of fact, there are some things I could do depending on what I remember from algebra about logarithms that might be helpful here. Let me go back to the other version up here. If I had ln of tangent, my brain says there's a u sub with the stuff inside, right?
Yeah.
So what if we made u equal to tangent of x? What's du?
Secant squared of x dx.
Great. I don't see any secants around here, do you?
Unless you do like 1 over cosine of x.
Oh, okay, wait a minute. So if I take this and I write it ln tangent of x, I still have the sine of x down here, and then I write 1 over cosine of x. That's better, because now I have a secant. But I want more than 1, right? I want secant squared. I need another cosine on the bottom, right? I can't just make it up and shove it in there unless I don't change this. The only thing I'm allowed to do that doesn't change stuff, I can add 0 or I can multiply by 1. I'm going to multiply by 1. But I'm going to write that 1 down here. Isn't it? One is cosine x over cosine of x. That's 1, right? So let's take the cosine of x that's in the top here and put it with this cosine of x. And we'll take the cosine that's on the bottom and put it over here with the sine. If I put this cosine with this and this cosine with this, that's how I get the cosine squared. What do I now have on the bottom? Because it's sine over cosine, isn't it? Still haven't done my u substitution, have I? I just kept rewriting crap and I haven't actually turned it into u's. Let's turn it into u's. What do you get? There, now I can still see the u sub at the top. Aha! And I can go a step further. What is the tangent of pi over 4? One. And the tangent of pi over 3 is the square root of 3. Nora, I have ln of u over u. How does that help me? Back of my brain. Rattle, 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 rattle. Rattle, 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 rattle. Hear those nesting dolls. What's the derivative of ln of x? Say again? 1 over x dx, right? This is another substitution thing and its derivative. So this is a 2-layer deep u substitution. I need to do another one. I would never have seen that from the beginning of this problem. But by seeing ln of tangent and seeing the inside and outside, that leads me to this where I see an inside and outside, but it's thing and d thing. So what is the new version of this integral in v? v dv.
Do you have to change your balance?
You don't have to. You could write u equals and u equals, then do the antiderivative, go back and plug in the old numbers. But that's why I changed them in the first place, because it was much easier. And I don't have to think about the old numbers anymore. Again, that is a personal preference. I am more fond of changing the limits every time I do a substitution than I am of going back and using the old numbers. But that's my preference. Doesn't have to be yours. If you change the limits, again, when you do the new integral, you just have power rule and you're done. If you don't, then you get the antiderivative, you put it back in terms of the logarithm, and then you plug in the numbers. No, I changed these numbers, right? So up here, I said x was pi over 4, so u was 1. X was pi over 3, so u was the square root of 3. Here I would say u is equal to 1, so v is ln of 1. What's ln of 1? U equals square root of 3, v equals ln of the square root of 3, which is going to be some sucky looking decimal. I'll just leave it like that. If you really want to, you can play with properties of logarithms and do all sorts of things with those to give you nicer looking numbers, or you can just give me a decimal. I'm perfectly happy with that. So Maddie, with that in mind, what would my new integral be?
Integral from 0 to whatever the heck of. You don't actually do the integral.
No, just write it down. What's the antiderivative? What's the no, that's the antiderivative. What's the integral? So there we go. And that's an easy integral to deal with. I like that one. One of the oldest actual original source calculus papers I ever read was one of the versions of the power rule done, I believe, by Brown, who was Newton's teacher at Cambridge. So the part that bugged me the most is the damn thing's in Latin. So I don't read Latin. My grandfather taught Latin. I don't read it. But I could recognize the diagram and the equation, and he does the integral of x dx. He does that problem. using Newton's method, well, what would become Newton's method of fluxions and fluents. He runs through the entire thing. And I'm laughing my ass off because I'm like, I don't know any of the words around this, but the math makes perfect sense. Because my grandfather taught Latin, I have such things as Winnius Puius on my bookshelf. Winnie the Pooh in Latin. Still can't read it, but anyhow, more questions.
35 on 7.5.
35 on 7.5. X over 1 plus cosine squared x?
Yeah.
Okay. This problem is here because I am evil. I need no calculus to do this problem. In your textbook, turn to chapter 5, section 5, where we did use substitution. At the end of the section on use substitution are two theorems on symmetry, page 417. Make a note if you don't have to go, page 417. What do the rules on page 417 say? Those of you that do have your book.
If f is even, f of negative x equals f of x, then the integral from negative a to a, f of x dx equals 2 times the integral from 0 to a, f of x dx. If f is odd, f of negative x equals negative f of x, then the integral from negative a to a, f of x dx equals 0.
And the reason these two rules were twigged in my memory when I looked at this problem is because that integral goes from minus pi over 2 to pi over 2. So I want to know which of those two categories this function satisfies. Is this function even or is this function odd? Now, turn the page. Page 418 shows you two pictures. And those pictures are the images of what an even function or an odd function might look like. A function that's even, f of negative x is the same as f of x. A function that's odd, f of minus x is the negative of f of x. So I need to know whether the picture for our function looks like this or like this. Graph it. What do you see in your picture? Make sure you're in radians. Please. We're doing trig functions. We have to be in radians. Your calculator should never leave radians. If you are a science person and you need to use degrees, there's a button for that. You don't ever have to come out of radians. Above the apps button, it says angle. If you hit second and angle, there's the degree mark. If you need to do something in degrees, use that. Don't ever leave radians. It'll screw up everything in calculus. Several of my high school students have told me that on multiple occasions they've had physics class and calculus class back to back, and the physics teacher wants degrees and the calculus teacher wants radians, and always at least one exam, and the AP exams that happens all the time. So what do I see when I graph? I have to turn that off. When I graph x over parentheses 1 plus cosine of x, then square it, then close the parentheses, I get picture where the left side, the left side is the upside down version of the right side, yes? Same picture. When I turn it upside down by 180 degrees, rotate it. That means we have this criteria. What's my integral? With no calculus. If you take a closer look at that picture, so for example, this is a zoom in on that picture, and you see this is only going from minus pi over 2 to pi over 2 this time, minus 2 to 2 this way. You'll see that this area over here between the x-axis and the curve, and this area over here between the x-axis and the curve are exactly the same visually, but the one on the left is negative, the one on the right is positive. They must balance each other out. Now, what if I don't have this? How do I determine whether the function is even or odd? I do this algebraically. But this requires me to remember something from trig. And that was a long time ago in a galaxy far, far away, right? I need to know which trig functions are odd and which trig functions are even. What do I do with that minus sign inside a cosine? Well, either it goes away because cosine is even, or it comes outside because cosine is odd, right? One of those two. But then I'm going to square it, right? If it goes away, then when I square it, nothing happens. If it comes outside and I square it, negative 1 squared becomes positive 1. Which means in either case, this minus sign is going to go away. Is this and this satisfying this equation? Oh, f of negative x is the opposite of f of x. I can also remember by looking at the picture of cosine in my head, hey, the left side and the right side of the cosine are the same. It's even, so that minus sign disappears. Now, only the minus sign on the bottom disappeared. Minus sign on the top stayed around. Minus sign on the top stayed around, and that's how we got the minus sign out front. Speaking mother.
So is there no way to do that calculus-wise?
I don't know how to do this antiderivative. I could figure it out, but I'm not sure that's going to be fun. Yeah, that's the problem with having that trig function and the polynomial together and having division involved there. I could probably do something with one of the trig identities, but it's 1 plus cosine squared, so it's still not going to be a nice trig identity. There are some other methods that we haven't gone through yet and many of them involve techniques I don't want us to do in this course at all. I think this particular problem is best addressed with something called the residue theorem. But the residue theorem is in a course called complex analysis, and that's Math 331, and that's an elective you take after Calc 3. I don't want to do that here. There might be another way. I'd have to look at several other sources and say, well, what could I transform that function into to make it easier? What substitutions could I do? What sort of integration by parts playing around could I do? It's in the bottom. Could I do something to get it out of the bottom? Probably, but it's not going to be simple. I have more on how to do things that when I look at this and I go, ooh, that we'll talk about tomorrow. But yes, at the moment, I don't know how to do this integral. Even if it doesn't turn out to be odd, even if it turns out to be even, that makes my integral simpler because it makes one of my limits 0, and plugging in 0 is always simple. So if you see the same upper limit, lower limit value, just one's positive, one's negative, yes, this trick should jump up in the back of your head and go, hey, look at me. I don't know why, but the visual imagery of an integral as an area under a curve stuck. And I am a very visual person. So geometry and algebra are two very different sets of skills. And people who are very algebraic are usually not very visual, and vice versa in math. And that, I think, Tom, that would be the problem. If you try and attack this algebraically, how do I make this antiderivative? You're going to beat your head against the table. But if you say, oh, wait a minute, there's a symmetry argument to be made here. There's a picture, and it might be the same if I fold it, or it might be upside down. Because the numbers match, poof, that jumps up. My senior year as an undergraduate, the actuary science program started at the University of Florida, where I was an undergraduate. And Bruce Edwards was the instructor for that. And the first exam the actuaries have to take, well, back then, the exam was a review of calculus and linear algebra. So we basically did 4 semesters worth of calculus review that spring. He needed a shill, somebody in the back of the class who guaranteed would be able to solve those problems. And I was a senior and a math major. He said, I want you to take this course. So I took the course. But routinely, I would get to problems like this, and he'd ask everybody, and he'd be like, I don't know what to do. And he'd look at me, and I'd be sitting in the back room, and I'd go, yes, I got this one. And he'd go, okay, well, come up and explain it, because that was what he was asking. We would do problems from the old exams, and he'd ask people to come up and explain them. And almost always, problems that were visual in nature to these very good sophomore math majors were not clear to them. They were technically very good at doing all the integrals and very good at doing all the algebra and very good at doing all the calculus, but they didn't see it. And so I'm really in favor of graphing everything, especially when I see matching limits. By the way, that was before my first graphing calculator. I got my first graphing calculator in 1993, and that class was in 1991. So I didn't have one at the time. More questions? That was a sideways ramble. Sorry about that. Yes, sir.
We do 52.
In the same section?
Yes.
So that's sine x cosine to the fourth? Oh, no, I'm in the wrong section. Whoops. x over x to the fourth plus 1? Sorry, 1 over x to the fourth plus 1?
Dx over x, and the x to the fourth plus.
Okay. All I did was pull the dx off. I look at that and I'm like, oh, this is going to suck because that is a rational function. It means I need to do partial fractions. But when I break that into partial fractions, it should look like that. Because you can't factor x to the fourth plus 1 without getting into complex numbers. Gosh. Jack, what's the top of the left fraction? Right, it's a number, a. The problem is the top of the right fraction. Because technically, it needs to be 1 degree smaller than the bottom. It means it should have x cubed in it, right? But it should also give me the opportunity to look at every power smaller than that. Now, if I'm lucky, a bunch of those will turn out to be 0. Hopefully, I'll get something that leads me to a nice U substitution. But that's the problem. Because now, when I multiply through that big, nasty common denominator, I get 1 equals a times x to the fourth plus 1 plus x times all of this. So over on the left, the coefficient of x is 0, the coefficient of x squared is 0, coefficient of x cubed is 0, coefficient of x to the fourth is 0. Oh, I'm going to have a whole bunch of equations to solve, aren't I? Let's see. On the right, I get ax to the fourth plus a, and then bx to the fourth, cx cubed, dx squared, and ex, and that's equal to 1. Gather your like terms. On the right, a plus b, x to the fourth, cx cubed, dx squared, ex, and a. What's the value of a? 1. What's the value of b? If I match stuff up, the a on the end matches with the 1, right? A is equal to 1. There are no x's, so e is equal to 0. There are no x squareds, so d is equal to 0. There are no x cubed, so c is equal to 0. There are no x to the fourth, so a plus b is equal to 0. That means b itself is not 0. What's b? Aha. So now I can go back up here and I can put those numbers in, and then I do get something that leads me to a nice U substitution. Whew. I'm guaranteeing you the calculus is not the hard part. Once we write out the partial fractions, all the algebra is the sucky part here. Better?
Yeah.
Yes. All right. Next to each of these equations, let me write something. Constant x, x squared, x cubed, x to the fourth. That's where each of those came from. The equation here is the part of the expression on this side, and the numbers here are the parts of the expression on that side. More questions? Jacob?
Wait, so for this, so then would it be negative x over the interval for s?
That's exactly right. Because it's plus minus 1x cubed. I like that one. That's a U sub. Every time I can take a problem that looks ugly, nasty, I don't know what to do, and reduce it to a problem I've already solved. Or even just acknowledge that now this is something I know how to solve, I'm much happier about it. A bad joke about mathematicians. A physicist, an engineer, and a mathematician are all asleep in a hotel, and one of the walls catches fire. The engineer, looking around, seeing that the wall is on fire, grabs the trash can in the bathroom, turns on the shower, fills the bed, puts out his section of the wall, soaks the bed, soaks the floor, drowns most of the room, goes back to sleep. The engineer, seeing his section of the wall on fire, goes over, picks up the bathroom trash can, fills the shower, turns the shower off, pours it over the bottom of the wall that's on fire, puff of steam, goes to sleep in a dry bed. The mathematician looks in the bathroom, sees the trash can, sees the shower head, goes, oh, there's a solution, goes back to sleep. I already know how to do this, I don't have to do any more. Yes, you do finish the problem. Told you it was a bad joke. Okay, so tomorrow I collect these two assignments and we'll talk about other methods and what those other transformations do for us and what do we do if we simply have no frickin' clue, like I don't even have even the slightest idea how to do that antiderivative. But we'll do it tomorrow. Yes, Leo?
I was thinking there that page like the chart would go to.
Oh, well,
Substitution.
let's take a look and see what we can find. But we'll talk about that tomorrow. I hope you all have a wonderful rest of your day. I will see you all then.